determine and to develop a DST, so a decision support tool. And the objective is to release this tool to peatland managers in order to optimize and to manage their site. So it is the overall modeling approach, and then I will describe the different part of this work. So as I said you, the model, we want to develop a model adapted to peatland scale, and which take into account all the specificity of the site to estimate the carbon balance. And then we will develop the decision support tool. So up to now, what we did in the CarePeat project, it is a first peatland inventory. So so for the 5 sites of the project, we collect all the available data that we can use then in the model. And now we are in the second phase, which is a development phase of the numerical tool with the calibration and the validation of the tool. And also we are in the of the decision support tool. And this is these 2 phases that I will speak today. So about the modeling approach. So first scheme to see what we want to model. Of course, everyone knows the complexity of such systems with many interactions, both in the unsaturated and the saturated zone, with many reactions, so geochemical and physical reactions, with the contribution, for example, also of the vegetals in this transfer, the role of the evapotranspiration, precipitation. So we have to first to conceptualize this continuum between the unsaturated and the saturated zone. And what we use, it is a code able to take into account all these parameters. So for example, in the gas phase, it will be to take into account the gas diffusion, but also the interaction between the gas and the water phase, and between the liquid and the solid. So we have to develop all these interactions. And in this program and this project, we propose to use the HPX program, which is recently developed by Belgium teams to model this system. So just, I will not present you all the equations. It is not the objective here. It is just to show you what we try to determine. So our objective, it is to both on the transport. So of course, with the main processes like advection, diffusion, dispersion. So this part is done by the transport code hydrous. And on the other part, we have a geochemical and biogeochemical code, which take into account all the reactivity of the system. And this code, it is a FRIC-C. So there is a coupling between these 2 codes, so with exchanges and transfer of information, and we are able to model the system. So this is just an introduction of the code, just to show you what we can do with this code, because it is a recent developed code, and it is never used, for example, for peatland systems. So we tried first this code on a generic case. So you have here, for example, a very simplified system with an unsaturated zone, a saturated zone. The water level is at 50 centimeters. So we consider a mean porosity. We consider in the system the production of CO2 and also the consumption of oxygen in this zone. We are taking into account the temperature and water effects, and we imagine a variable recharges conditions. So you have on this figure, you can see, for example, a random generation of effective recharge with dry periods and periods with more important recharge. And we calculate the water, gas, and temperature transfer in the unsaturated zone. So just to show you some results, but it is really the beginning of this application. So of course, according to the recharge condition and the position of the water table, so it is the black line here, we can follow, for example, the evolution of the water profile according to time. So here it is just a simulation on 1 year, and we can follow, of course, the evolution of this water profile. We have also the possibility to follow the evolution of temperature of the systems, both in the saturated and the unsaturated zone. So of course, all of this depends on the boundary condition that we took at the beginning, but it is just to show you that we are able to manage all these systems. We are able also to follow the gas transfer in the unsaturated zone. For example, here with partial pressure of oxygen, we see, for example, here the total consumption of oxygen in the first centimeters of the system. And to finish, we are able to get between peatland and atmosphere with, for example, here, a daily production of the CO2 for the system. So of course, it is modeling in 1D dimension. So it is on a given surface. But what we see, for example, so in blue, it is the daily production of CO2. In orange, it is the cumulative CO2 fluxes. But what we see, for example, here at 230 days, we have an important recharge period. What we see, it is the decrease in CO2 fluxes, whereas in the between 250 days and 300 years, we have a dry period, and during this period, we have a high production of CO2. So we see that it is consistent with the fluxes and the recharge of the system. So of course, now the next step it is to use real data, from sites. So we will integrate historical data of temperature, water level, and so on, just to try to reproduce the real data and to see if we are able to obtain the carbon emissions measured. So this is what I want to show you for the modeling part. On the second point, it is so the development of the decision support tool. So the idea here, it is really to provide a DST for the manager. And what we want to propose, it is a tool able to map the carbon sink and sources zones, so of the investigated site. So the approach is based on the GIS approach, Geographical Information System. And what we want to propose, it is something with a rapid visualization of the site in order to really identify the different parts of the peatland and which zone are where we have some emission and where we have some absorption of carbon. And the idea then it is to give this tool to the manager to optimize their site, for example, by proposing some scenario. For example, we can simulate some long term dry out. We can simulate some modification of vegetation just to see if these changes have an impact on the carbon fluxes. So, of course, to do that, we need some work before releasing this tool, and we need to characterize the sites by trying to interpolate the relevant data. So we are working on different parameters. So for example, of course, we are starting by the digital elevation model. So by some interpolation, we can reproduce the topography of the surface and the elevation of the surface. We have to, from this digital elevation model, we can determine some hydrological products, like, for example, the slope map. So this is very interesting to determine this because it will give some information on the infiltration of or on the runoff of the recharge. From this data, we can also deduce the topography wetness index of the soil. So this is also quite important because we see that the CO2 emissions are related to this wetness. So of course, it is some information that we will include then in the calculation of the fluxes at the size of at the scale of the peatland. And also determine and calculate the theoretical Talweg network. So it is from the digital elevation model. So we can reproduce also according to the rivers and artificial drains. We can reproduce the hydraulic condition of the site. So all of this, it is on the Laget site that I show you the example, but of course, that are involved in Carpet. About data, here it is, for example, the IDPR, which is an index of development and persistence of the river network. So it is an index to give some information on the surface water infiltration and runoff. So in this case also, it gives some ideas of the part of the peatland where we will have mostly infiltration and where we will have some runoff. Of course, we include in this data the water table. It is one of the main parameters. So here we have the chance to have a campaign of measurements where many measurements have been done. So it is, of course, easier to determine the map and the position of the water table. Of course, we have also the pit thickness to determine. And so the last information that we will include in this system, it is also the information on the vegetation. And for that, we use the drone data. So this drone data have been acquired in Carpet project. So it is our colleagues and partner from Ireland who made this. So from this drone measurements, we can determine the digital elevation model. So including in this case, we are including vegetation. And from the digital elevation model and this one, we can deduce, for example, the NDVI, so the vegetation index at the peatland scale. And then by crossing this information with the BD topo from the EGN, we are able to determine the zones with different vegetations in the system. So at the peatland scale. And here it is refer to different zones in the at the peatland scale. So all this information, you see, it's quite it is many information and different information, because we have information on the subsurface, we have information on the surface, but all of this will contribute to the final calculation of greenhouse gases fluxes. The idea also it is to integrate satellite data and then to produce, of course, CO2 and methane fluxes maps. So all this work, of course, it is in progress. I cannot show this is the next step that we will do in the next month. And just to finish, our main question also, it is, okay, we are developing this numerical tool, but how we can provide this information to the managers. So it is really a question. So just to show you what we can do, it is, for example, to provide some interactive and dynamic PDF file. So I can just show you an example. It is I don't know if you see those.
We do.
Yeah, okay, perfect. So you have here, for example, a dynamic PDF with different layers. So it is possible, for example, to play with different layers. And for example, we can add some information. You have here, for example, the slope map that I showed you before. You can add, for example, the wetness index. You can add the drains, the rivers. And so the idea, for example, it is to propose some scenario and the manager with this file, and to imagine some calculations of GHG fluxes. So this is something dynamic that we want to release to the manager at the end of the project. So, but we have some reflections and some discussion about that, because of course you have the possibility to have some PDF file, but we have also online version that we can also be used. So it will be decided during the project. So this is what I want to show you about the modeling approach in CarePit. So of course, we don't have final results, but it is our global objectives. And so if you have any questions, answer.
Yes, thank you, Laurent. I think we have some time for specific questions for Laurent. I see there are some questions already in the chat regarding to Twan's question. Is it okay, Twan, that we keep this for the synergy discussion? Yeah, great. Then there's a question from Jasper, I think, to Laurent. This is very complex. How will you calibrate and validate this?
The difficulty, of course, of this model, and more we have data, and better will be the calibration. It is so we started by Laget, and this is why I show you some data on Laget. This is why we have some data already available, because we have some recording of data since 4 or 5 years. For example, information on the water table, on temperature, but we have also eddy covariance measurements, so with CO2 and methane measurements. So, of course, if we have this data, I think it will be easier to calibrate and to do that. So, but of course, it is very dependent on the site. And we are sure that the observation that we have, for example, site will be referred to that region or in an island. So, of course, so we hope that we will have major elements and major parameters, like, for example, the water table, the temperature. We know, and the vegetation, we know that these three parameters are the most important ones. And then we will see if we have some additional calibration to have in this model. But of course, yes, the most important, it is the acquisition of data.
Okay, thank you, Laurent. Another question is what input are needed for this model from Amé?
For the first part, for the numerical model, the most important, it is the water table, the peat thickness, the temperature, and if possible, the CO2 fluxes at the interface, just to calibrate the model. It is the main. Of course, then we can add, if we want, the chemical composition of the water, of course, we can complexify the system, but at the beginning, yes, it is mainly the water table and the variation of this water table, the temperature, and the kind of vegetation and the peat thickness.
Chris Field, you raised your hand.
Hi, yeah, thanks. Interesting stuff, Laurent, and I think I'm really interested to understand sort of the trade-off between the data needed for the model and the accuracy. So when we're looking at large, say, landscape scales, it sounds very attractive. I think for if we've got a peatland somewhere, the main parameters you talk about, like vegetation, water table, and maybe temperature, I think could be quite easily provided by a peatland manager, and it would be really interesting to sort of see how gets you to a how for the data. I just wondered if you'd trialed it at Lagoette and you'd maybe looked at the addition of incremental variables and what that did to accuracy. So if you just run the model with water table, temperature, and vegetation, does that get you close to the approximate gas fluxes that you've recorded at the site? And then how it then improves. I guess it's a case of diminishing returns, isn't it? The more data we add, each variable doesn't do as much. But I think for large landscape scale application, it'd be interesting to understand how accurate it is from these few variables.
You're right. I think we can distinguish two things. For the model, the numerical that I show you, it's right that it is quite mechanistic, and what we propose it is to go a little bit further in the detail and to use the maximum of information. Of course, if we have the possibility to integrate in the model the composition of the water, the composition of the gases, and so on. Of course, we will have something very realistic, and I think we will be very accurate, but it will be very localized. For example, on 1 square meter, of course, we can determine accurately what is happened in this limited area. And then I think the difficulty here it is the upscaling, how we go from the 1 square meter to the peatland scale. And this is why we wanted to use the GIST approach. It is ready to say, okay, from the model, what we observe, it is, for example, that in this part, in this zone, we have this behavior of the system, and in this part, we have some emissions, and in this part, we have some absorption, for example. And what we want, it is, I think it is important to visualize at the peatland scale, okay, this zone, it is different than this one, because the difference, it is due to the vegetation, to the water table, and ready to see, for example, if we want to imagine some restoration scenarios, we have to focus mainly on this part and not on this one, because this one, the behavior is quite okay, but this one, so we have, my idea, it is just to see where are the most, for example, degraded zones, and what we have to focus on this zone. And this is the initial idea. Of course, we will lose some accuracy by jumping at the peatland scale. Of course, we will not be able to model mechanistically or the mechanism at this scale, but we will have, I think, quite representative values.
Yeah, thanks, Laurent. I think given the fact that when we use an emissions factor, we just take one emissions factor for a whole area of land. I think it's quite nice if we can get a bit closer. It'd be interesting to understand how the interaction between the water table term and the topographical wetness index, because that could be a real tool to taking this to a landscape scale, because we can do topographical wetness index over large regions easily.
Yeah.
Yeah.
Yeah. Yes, but we can compare. I think we can compare what we obtain by the measurements and what we obtain by the calculation, just to see, for example, if we are in the same. Yes, the similar values or not, because of course, as I said, it is one of the parameters that have an importance then on the gases fluxes.
Thank you, Laurent. There are 2 questions popping up in the chat. I propose that you answer them also in the chat, and that we continue with the next presentation. Presentation from Jasper van Belle. He is working in Interreg Carbon Connects and Canopé, and he will be presenting the site emissions tool. So Jasper, the floor is yours. You can share your presentation.
Yeah, we'll do that, I think, once it works. Yes, share screen. You should now all be seeing my second screen.
Yeah, perfect.
Okay, good. Well, this is work that we've been doing within Carbon Connects, and I'll be talking about why is this not working? Yes. Which is, well, the consortium is here, and I seem to have lost my title slide somewhere. I will be talking about what we've been doing to model or actually quantify ecosystem services. I've been grown. Well, my thinking of this has developed into that. I'm now calling this more calculators because the approach is very different from what you just saw from Laurent. Approach, we're constantly searching for a balance between simplicity and accuracy here. And so our goal with these calculators was to give a decent estimate of, well, for instance, carbon fluxes, which is what most of this talk will be about. This is one of the products that we've been developing so far, and I just wanted to show you this to you so that you're aware that we've been building this. This is a peatland map, which is basically just an amalgam of national peat soil maps and just taking out the PT parts of it. What we want to achieve in Carbon Connects is that we want to develop business models based on the product use, but also on carbon crediting. And this is what most of my talk will be about, but also on construction. So what we've done to quantify the greenhouse gas emissions is that we've built in an Excel tool that we call the site emissions tool. And it estimates greenhouse gas emissions from your site depending on vegetation, groundwater levels, peat type, and whatnot. And a central core element of this is the existing guest model, which should actually, when building this presentation, you're all familiar with. But if not, it's basically a database of recorded, measured greenhouse gas emissions or yearly annual emission budgets, which has been broken down into different types of vegetation and the groundwater levels associated with this. So that you basically get type, for instance, a wet grassland or a semi-dry grassland or a bog vegetation or a heather vegetation. So that's what we've been using as the basis for the carbon fluxes. What it does, the site emissions tool, is that it calculates CO2, methane, and N2O fluxes, translates these to CO2 equivalents, and the idea is that we aimed it to be applicable in managed peatlands. So we also include the management or the activities that are undertaken as part of the land. And we also included the use of biomass, because if you use your biomass to, well, for instance, replace fossil fuel use, you could count this as a greenhouse gas reduction. And that's and that is the ultimate goal. We want to set up a reasonably trustworthy foundation to base carbon credits claims upon. And as it is with these type of where it compares situations, so basically the do nothing scenario, and it compares this to what changes if you do change something, for instance, your land management or your water levels. And then the difference is what you can claim for payment schemes. The carbon fluxes that come out of the land, specifically, well, it needs to be said that we've only included carbon fluxes directly from the soil, and this is based on an extended version of the guest model, which was provided us very kindly by the John Kouwenberg et al. So this is an extended version that has some 30, well, let's say standard um, greenhouse gas emission site types, which is what the guest stands for. And it has 9 highly specific types, for instance, ditches or a simulated harvest in sphagnum cultivation, those type. The guest or the site emissions tool that we've built, the blue and white figure below is a part of the input. This limits the amount of the options for the vegetation classes, or actually the guest types that could possibly occur with this groundwater level. So the groundwater level is the first selection, the first filter, and then the user needs to select the best fitting vegetation. And what you see here is that the top box is the baseline scenario approach. In this case, I filled in some numbers for a pilot site that VHL is working on, and there it has been transferred from a rather extensively used moist grassland vegetation to a taifa plantation. Then the carbon fluxes from soil. If you look at crediting schemes, you can only claim the amount of carbon that is actually in your soil. So if you're looking at reductions of emissions, you cannot claim prevented emissions indefinitely. This is restricted to the amount of carbon that would have been going from your soil in the baseline scenario. So to deal with this, it is actually in the soil. So the user is asked to input the peat depth average in the site and the peat type. And you, the site emissions tool then uses the table that you see here to estimate how much carbon is actually in the soil. And in the end, it deducts the carbon emitted from the soil from the carbon stock at start. And then once the carbon stock is depleted in the baseline scenario, you can no longer claim emission reductions in carbon flux from the soil. N2O is not included as a flux from the soil, but only as resulting from fertilizer applications, manure, crop residues, etc. And it well, I'm tempted to say simply, but it's not all that simple, but it simply applies the IPCC Tier 1 calculations to determine the amount of N2O emission that this results in. So again, you see here the input field for the user. One can input how much organic or animal manure or organic fertilizers is brought into the field, or synthetic fertilizer, where a choice has been made between, or needs to be made between, ammonium-based and nitrate-based. And then because animals also produce droppings, of course, they produce their own manure. So even aside from specific manure application as a fertilizer, if you put animals in the field, they will produce manure, and this will affect your N2O emissions. So this is included as well, where the user selects the type of animal and the number of animals present in the site and the amount of days that these are there. If a crop is being harvested, um, the crop yield or the harvest size, if you will, needs to be filled in, and it needs to be indicated whether crop residues are left on the field, because as per the IPCC calculations, the crop residues are a source of nitrous oxide emissions. Um, so that's basic. This is actually the part that asks most inputs from the user. This is just for the baseline situation. You have a similar input screen for the rewetting situation. So on the next step is to put in the amount of diesel or electricity usage that is associated with the land management, which is then calculated into the associated CO2 emissions. So, for instance, if you go from a standard agricultural field with, as you can see on the left, grass being mown, this, of course, the tractor used for this will consume diesel. But once you change this into a polluted culture, you will still be needing machinery and the substantial source of energy usage. So we take this into account as well. Finally, the product use or is taken into account as well. So, for instance, if you use the harvested product as a fuel source, um, you can claim CO2 reductions from this because you replace the fossil fuel use by a biomass use. Um, but another application that is very interesting is the use in long-term applications, for instance, building materials. What you see in the picture on the left is a standard house. On the right is the bio-based pavilion, which was presented during the Dutch Design Week last autumn. And this is a small building that was built entirely from taifa and rice straw with fungi and some timber in there. Um, um, so this is the promising new future. If you succeed in using the biomass for these bio-based building materials, then the carbon in the biomass is stored for some 25, 30, maybe even longer years. So you can claim carbon storage for this. So basically, this is an attempt to simplify an LCA approach to determining the effects on greenhouse gas emissions once you change your land use. A few things are not included. The most prominent one of this is site preparation. So if you start to remove your topsoil, this is not included, but it will have a large impact on your project. And similarly, we have leakage effects and some more. I had planned to show you very shortly, if I can do this. There it is. Give you a short demonstration. This is the output screen that you're seeing here, and on top you see a few simple site characteristics which are mainly used to, well, present a comprehensive overview to the user. So this is basically used for your own administration purposes. And then you have the outcomes. Here you see an outcome for the baseline on top. So this is the do nothing scenario, and it tells you how much comes, what are the carbon fluxes from the soil according to the gas model. The result of the N2O calculations is shown here. Activity is what you use in fuel and energy use, and this is the total emission for the entire site. This is just a half-hectare site, so the emissions are pretty low. Plus, it is an extensively used site, and this is a graphic representation of the same. Each color represents a different flux. So if you then look at what changes after rewetting, is that you can immediately see that the types of fluxes are changing. And there's not much happening to the N2O because it wasn't much to start with, and it's still not much is happening there. But what you can see is that the light green is being replaced by dark green, and this is the always um, well um, difficult transition from CO2 emissions to methane emissions. But what you also see is that the zero is here. So we have negative CO2 emissions, and we have the blue is savings from product use. This wasn't included in the baseline, but in the outcome or in the rewetting, it shows you how much you are saving by the application of your biomass. So the net equation of all this for this site is that it turns from around let's say 11 ton CO2 equivalents for the entire site per year in emissions to minus zero point 0.5. So it turned from a net source to a net sink. Then all the way to the bottom, there are some summation screens giving you the total net greenhouse gas savings per site and per hectare and the stock. So this is basically what happens to the carbon in your soil. And some more of these product use again. And here is in the bottom is the carbon stock in the peat soil at the start year, which was in this case calculated to be 328 ton CO2 equivalents or 89 ton carbon for this half hectare site. And in the baseline emissions would have led to disappearance of the peat within 34 years is the estimate. And in the rewetting scenario, this is changed to a very flattened, but I cannot seem to change this, a very flattened infinite sign, which indicates that we've turned a carbon consuming land use into a carbon buildup land use. So we have net carbon accumulation indicating new peat being formed. The graphical output on the right is a timeline starting at the year that the rewetting started, 2015 in this case, and running up into 2050 because, well, when building this, um, the idea behind this was that there's a time horizon at 2050 because by 2050 we're all supposed to be net carbon neutral. So by that time, business as usual cannot be net emitting anymore. So the standard policies will have reduced the emissions to net emissions, I must say, to zero. So then you cannot claim anything else because of the additionality criterion in carbon crediting. What you see here is the blue line is the emission in the rewetting scenario. The green line is the emission in the business as usual scenario, and the orange line is of course the difference. What is interesting is that it dropped sharply at around 2000, I think, 48. This is because in the business as usual scenario, all the peat will have been lost by 2048. So After 2048, no carbon emission reduction can be claimed anymore, but you can still claim the carbon or the emission reductions resulting from carbon sequestration and from the product use. So for me personally, one of the lessons from this exercise, from building this, was the importance of the product use that you actually choose for your rewetting project. Because if you just use this for animal feed, for instance, you will not be able to claim any reductions from this, and it can be a substantial amount when you compare this to the rest of the project. So that's the short overview. Then there's some other stuff that we're still working on, which is what we've called the blue credits. Basically, these are the other ecosystem services that are associated with rewetting in peatlands, and we want to translate these into tradable credits as well, so that you can include them in a crediting system or a subsidy system, or whichever is your choice. The picture on the right shows that if you want to include these additional ecosystem services, you need to figure out or decide whether you want to do an explicit or implicit combination of ecosystem services. I'll not be going into that right now, but what we are working on right now is water quality improvements. So that's the nutrient scrubbing from polluted cultures, and the water quantity effects. So water storage for dry times and flood reduction during very wet times. This is a preview of what we're working on for the water quality reduction tool. The nutrient reduction tool, I've called this in line with the site emissions tool. Actually, I just came up with the name last night. This is, well, basically what we're doing here is we're trying to bring down the huge complexity to manageable proportions. So we've identified three main processes. You have the bacterial processes, which are actually only helping to remove nitrogen, and this is mostly temperature dependent process. Then we have plant uptake, the vegetation growth, and if you harvest the vegetation, you of course export nutrients. This exports both nitrogen and phosphorus. Below is a graph of the relation between the biomass production and the P removal, and you can do the same for nitrogen and potassium for Phragmites and Typha. And finally, and this is, we have a first version of this working now, but it doesn't include the sedimentation part yet, which is shown here in gray. Sedimentation is basically the solid particles in your surface water can sediment, but it's highly dependent on the type of sediment that you have, and water depth, and retention time, and so that's a bit more complex. I haven't found a good way to simplify that any further yet. This is something that we're doing together with another project we're involved in, called Better Wetter. Actually, the first version of to make this applicable in a wider set of landscape types for carbon kinetics. And then we have the water quantity, which I termed the peat hydrology tool, but I'm not sure that's a very accurate name. Maybe it should just be the peat water tool, or if you have any good suggestions, please let me know. This is actually, a lot of work on this is being done by Ame. He's doing the modeling in a Hydrus 1D model. I think it's sort of similar to what Laurent showed us, but much simpler. And the idea is that if you have a peat column, you have a water level in it, and whether it rises or falls depends, of course, on evaporation and rainfall patterns. And once the water level rises, so basically, AME is modeling the water pressure here, which can be translated to water levels. And once this the wrong way. Once you reach the surface level, you'll get overland flow, and this contributes to, of course, flooding in rivers and all that. Um, we're still building on this. The central parameter that we're using for this is the bulk density. Bulk density is simply the mass of soil that you have in any volume of soil. And if you look at peat, there is as you can see on the right, a very clear relationship between hydrological parameters, in this case, the macro porosity and bulk density. And this is related to that if you um, will drain your peat, the peat will start to degrade and it will become more compact. Hence, your bulk density will increase. So the bulk density can be used, thanks to the study by Liu and Leonard shown here. The bulk density can be used as a central parameter, and it's or an indicator of a whole suite of hydrological parameters. It is fairly easy to determine in your site, and it responds to peat drying. So this is why we've chosen this as a central parameter. But this is all still work in progress, and well, that's it. Any questions?
Well, can I ask a question? Very interesting about it. I think this is potentially very useful for well, nature conservation organizations like Natuurmonumenten. I was wondering, you showed well, two scenarios, the baseline scenario and the project scenario. Those are in fact stationary situations. Is there also a way to include the time dependency in the scenarios?
No, actually,
Because
well,
we
not in these scenarios per se, but what you could do is simply just run multiple simulations for several years. So that I've been aware of this need. But if you want to do that, it very quickly becomes much more complex and it asks more inputs from the user. So we've kept it very simple with a baseline and a scenario or a rewetting. But of course, you can do multiple simulations for different years, and then just well combine it into a dynamic simulation, if you will, yourself. Yeah, but that's
okay,
the only
yeah.
way.
Yeah. Okay. Well, my question comes from well, we are preparing a carbon credit application for the Vochtelo Veen in the Netherlands, and then we have scenarios for the hydrological development over time in the baseline and in the project scenario, the restoration scenario. But well, maybe it's a good suggestion what you say that that we just apply that on well, the different hydrological inputs on for each year and create a time series ourselves.
Yeah, if you're very interested, I mean, we can adjust. Of course, it's just an Excel tool. It can be extended to include stuff like this, but this is not the standard version. Yeah.
Yeah. Well, and the same question, and I think that was also mentioned in the chat, is the spatial variation in an area. Like there are many gas types within one area.
Yeah.
And, so your suggestion is the same. Apply the Excel model on each gas type.
I'm afraid that's the only way. Yeah, yeah. So for now, basically, it's a similar approach as taken in the peatland code. You will need to identify more or less homogeneous units within your site yourself, So if you're looking at an agricultural field which is nicely leveled, etc., you might be able to do with just one simulation run, and otherwise you'll need to do several. Yeah. Any other questions? Maybe.
There's a lot going on in the chat.
Yeah. I just opened
Maybe
it.
you can catch up. I think I can highlight one or two questions that are still open. There's a question from Chris Field. How is new data added to the model when it becomes available?
Well, I guess what you'll have to do basically, this will mostly be the carbon fluxes. So that is in this case the guessed part, which actually is just tabs that is in the model. This is not visible to the welcome screen and an input screen and an output screen. But of course, there are some 15 other tabs that are, but you could relatively easily replace the numbers in the other numbers.
Yeah, I suppose I was thinking if we might have had maybe as new data as we do new studies, but also if we have site-specific data when we've measured stuff actually on a site.
Yeah. My main questions here, and this also links to the earlier question by Tuan Laurence or Capit's work can be used to calibrate this site emissions tool. Basically, the carbon flux is northern German database. So that is a point, well, that you need to keep in mind. And actually got a few students working on comparisons of fluxes across Europe. Because I'm not quite sure whether are still relevant for instance, the UK or Ireland, because the climatic conditions are quite different. And also, of course, in the gas model, it doesn't differentiate between peat types, for instance. So the difference between peat types is only there for the carbon content. So there's a lot of stuff that is not included. Yeah. Anything else? I just opened the chat function, so I'm still struggling to get an overview of the most important ones, including carbon offset, value of biomass. Yes, I guess if you but then if you grow a lot of timber, actually, peatlands are not included in a guest. So I don't think you would be able to apply this model in this case. But yeah, if you simply look, I mean, the main purpose of this site emissions tool is to support carbon crediting or payments. So yeah, you could actually think of scenarios where you, due to the product use, you can claim huge savings while still degrading a peatland. Yeah. Is there a way to adapt the set tool to estimate sequestration? Actually, yes, this is included via the carbon fluxes. So this is then if you have a negative carbon flux, then of course you have net sequestration, and this is included. Water pumps can be solar driven. Yeah, then you have 0 kilowatt hours. So it doesn't add to your emissions. Other machinery, I think the same goes. My main concern here is that you might have a machine running on gasoline, on non-diesel fuels, and you'll need to translate this because we have only diesel in here. Added in the future, I don't know. Fuel use, yes. How effective is this model in upland blanket bog? Yeah, this is of course related to my earlier remark that I'm not quite sure how applicable the guest in these blanket bogs. And this is actually specifically one of the cases that I've put a student on, but of course, um, as with all student projects, you always, well, you can't have too high expectations. So we'll see what that gives us. But I have become quite aware that the upland blanket bogs are quite different from our lowland raised bogs in terms of hydrology and for problem of climatic conditions and by consequence also the greenhouse gas emissions. So Harry is correct. Yes.
Talk
go on.
a
Yeah,
little
yeah.
as we go to the next presentation because we are quite late, but that's no problem. We can still answer some questions in the discussion session as so for now, I would like to give the floor to Andreas. You need to restore also on modeling and measuring gas flux.
Yeah, hello everybody. So I'm very impressed about the huge work on models and greenhouse gas fluxes. So I hope I will not disappoint you because we have only a short presentation because I come from the field and now I have only a few slides to show us what we do in live peat restore. And yeah, for me, I'm a geoecologist and I'm very interested in how the different landscapes act in part of as a sink of greenhouse gases. So for a couple of years, I work for NABU in a very small. I hope I will not boring to you. So because we have only a few slides, so maybe I here. Yes, you can see it.
Yes.
Okay. Okay. So yes, first of all, it's good to know that we have not our main goal is not to create or develop a product or tool for some stakeholders because we have the clear task to assess our work regarding to the greenhouse gases in our whole country project countries rights, and it's not embedded into a tool what we can use after this project. So let's see where we are. So Andis are here from Latvia. These are our country sites or our project sites. We have to restore a lot of peatlands in Germany, Poland, Latvia, Lithuania, and Estonia. So we go to the eastern part of Europe, and we have a project timeline of from July 2016 to December 2021. And you see, we have a 6 million project budget, but we have a very small part only for greenhouse gases and modeling. So this is not our. I remember you. We have not the biggest part is not modeling, but I have now the problem or the task to create or to calculate the fluxes from all our project sites to get an idea how much will be saved in the next years with our restoration measures. It's a big deal because if you have not so much money or tools to calculate, you have to find a way how to do it. So what we are where we are doing, you see here a table about our project sites where we measure greenhouse gases. It's very heterogeneous because we have very different ecosystems, very different peatlands, and in the whole areas, and we have to think how to gather information about from them. Yeah, what we are doing is first of all, we have also a data collection part. So we have to collect water table information, very much information about the vegetation, and then also came up with the greenhouse gas emissions. And practical, we restored 5,300 hectares. It's a main goal. It's the most part of the budget. And then the EC comes to us and asks us how much greenhouse gas we save with this restoration. And then we wrote in the proposal that we want to use also the guest approach. And EC said, okay, guest approach is good, but you have also to measure greenhouse gases without any more much money. So that's our yeah, initial stage. So we have to think about, okay, we can do it, but now we see there are a lot of different problems. If you only use a model without any field data, you cannot model extremely good. So we have to find a way to get field data and then to try to model it a bit. Yes, so we use the guest approach, and thanks to what was the name, Jasper, to explain a bit the guest model. I think all of you are familiar with this approach, but we started in the different countries that our partners are not very familiar to the guest approach. So the first thing is to translate this German-based or German by Kauenberg, explain to them how it works, how we can use it maybe, and maybe also how to look what they have as the guest types in the different countries. And the first problem in the partner countries was that we have different definitions about what we can find in the as guest type. We have maybe one of them say, okay, we have a bog heath, but the others say, okay, that's not a bog heath, that's more or less a moist meadow. So this is the first problem to find the same names, the same tables, and it was one time for 1 year to get to one common approach. Yeah, then we're setting up fixed plots and measuring points for vegetation, water level, and additionally also for gas measurements. Yeah, and the gas measurements started in 2018 and 2020. Here you can see, yeah, that it was our first system with a colleague of Latvia. We have before, we have find sea lava that was constructed by a company in transparent chamber design with fans and the thermometers inside the chambers, and we can measure both the eco, the respiration, the ecosystem respiration, and also the NEE, network ecosystem exchange. And here you have the Latvian, one of the Latvian sites. A lot of stuff outside this site to measure only this two CO2 fluxes. And additional to that, we also have to measure methane and N2O, and we have also to do it. And we use larger chambers also in Poland and Germany. And now we have our new partners, Silava. Here you can see Andis. he is also here in this meeting, and they use a little bit other chamber systems. And here you can see the Estonian ones. They have a different approach. So we have another problem in the beginning of our measurement with our measurements, because we have different chambers, we have different approaches, and we have to find a way how we can calibrate, or we can make it comparable to the different sites. So we use on one hand we have big chambers, we have small chambers, and we now also see that the fluxes are also very different. It's clear we have different vegetation periods, we have different methods, and this is another point. We have to make the experience that it's good to have in the beginning of such a project, and if we use different systems, we have to compare it in the very beginning, so that we can say, okay, the system errors or the system approaches so and so, and so then we can quantify the errors. But okay, the time goes on, and we are in the third year. We can start with the measurements also in Latvia, and we produce nice fluxes also in Latvia and Lithuania, and the Estonians do this also. Yeah, but it's, the chamber measurements are only single plots, so that's another problem for evaluate model data such as guest, because the EC said also you have to measure directly the greenhouse gas fluxes, because we are not what do I say? Um, they not trust the guest data, because it's a database from different sites in Germany and mid Europe. So we cannot say it, or that it's also match or fit with the Estonian or Baltic countries. So we have to measure greenhouse gases to compare it with the guest table. Yes, and this was another task. We have to use it. Yeah, and then we have the first year we look what we have as vegetation in the different countries to transform it or transfer it into gas types. And there we have the problem that we find a lot of areas with forested peatlands, and in the guest approach we have only open peatlands. So we have another problem. 50% maybe, or 60% of our project areas are forested, and yeah, and we have to find a way to come to an assessment how much greenhouse gases will be go to the atmosphere. And so we use a combination of emission data from open peatlands and sequestration by the trees for the calculation of the emission of the forested gas types. There's also another approach in Germany by Spangenberg. She prepared a paper where we can combine the different gas types and add it or combine it with the sequestration by the trees. Yes, and we also use then some scenarios where we have a baseline scenario where we have the current emissions of the project site that remains relatively constant on the time period. And the time period is also a most important thing, because you see, say, how much greenhouse gases you save in 30 to 50 years. Yeah, and we have no succession. So this is one of the main ideas to find a way how to come to a baseline scenario or to assessment with all countries to calculate the current emissions. So we use this baseline scenario as a state of the art. scenario to find a way, okay, how much gas type we have, and then we calculate the emissions from our project sites as a baseline. And then we create in the different project regions the current restoration scenarios that take into account that we have maybe a die-off of woods or forests, or we have active cutting of woods. And we have also scenarios with an development of the water tables in the different project sites, and calculate the amount of saved greenhouse gas, or the amount of greenhouse gas emissions based on the different gas types. So yeah, it was a very hard work for us, because nobody of our project partners had an idea how to do it. And yeah, and the estimation of the reduction potential, and this is the main result of this scenario work, is if we revet our maybe forested a forest stand, maybe with reduced productivity. And we have another scenario that we have also forested peatland with a more strong revetting. There, maybe the forest stand die off, or we have deforestation. Yeah, and nobody can say, and this is a big problem also with our partners, what's happened in the next 100 years. So nobody knows. And as an example for our German very small project site is here you see five to six different gas type. Here the legend is missing, sorry for that, but it's all of that is forested. It's only distinguished by the water level. We have very moist to wet peatland forest. Then we have a moister one, and we have a ditch here, and we create a map also from that to find out what is what happened in the next years. And then we have the different gas types here. You can see this. Some of them are taken from the updated gas catalog, but we have also to find different references for other gas types. What's not included in the catalog. And here we have also mesotrophic, eutrophic, moist forests, and also for our Baltic project regions, oligotrophic forests and shrubberies. We calculated the area which covered the sites with the different gas types, and then we have kind of a emission factor, or a gas factor here. And we come to the emission. What is there's a sum up what the calculated emission for the next 3 years, and then we have another what is as global warming potential for the next 50 years. So yeah, this is in total 4,000 for this only for the German side. This is the calculated sum of emission what in the next 50 years go out. Yeah, and the project scenario, we expect here in this location and water table increase of 25 to 37 centimeters in the northern part, and the southern part a maximum of increase of 50 centimeters. That means that the moist parts will disappear and replaced by very moist forests and shrubberies, and vice versa. We have another really simple gas type development for our restoration scenario. We have here now not more moist forest. We have only very moist and wet forest. It's what we expect from the restoration path. And then we have another emission global warming potential in the next 50 years, what is yeah, now with the minus here. Yeah, but how we take into account the forest, because this is all on the emission factors from the open peatland, from the guest open peatlands, and now we try to find a way to take into account the forest biomass, the forest carbon biomass, and there are a lot of different approaches, and we have to do it very simple, that all of our partners can do it. So we have take this equation. There are a lot of different approaches or equations to get the fixed carbon wooden biomass per year. Here it's included the volume, the basic wood density of species, and they have the BEF, the biomass expansion factors for conversion to stem biomass to above ground tree biomass. And we have the root to shoot ratio and the carbon fraction. It's very simple approach. Most of the data we can find in some tables, but if we ever can do, we have our own forest inventory data to use it also for this calculation. And together with the emission from the open peatlands, we have to combine these both approaches to get an idea how much carbon is saved in our in our above ground biomass in the forest. Yes, yeah, and you know, no lesson learned. I have no idea why it is here. I see this. The most important thing is that the most problems we have in this project is that we have missing data in the carbon in the guest catalog. We have the problem with the carbon calculation of the woods, and also the problem that we have not the money or the budget to get some information about the greenhouse gas measurements. Yeah, I have no idea what's now here, because this is not my presentation. So some results preliminary from the last 2 years. It's about the greenhouse gas fluxes in the Biesenthaler Basin or Becken. This is our German side. We have here plotted the different greenhouse gases as hourly data. It's not not annual balances. It's only the measurement day. We measured to different conditions and have, you see, a time course with higher respiration in summer and lower respiration in the springtime. There's a lot of potential because we have a lot of data also from Latvia and Lithuania, but we are now calculated the fluxes also from the whole sites. But again, we have only information about one plot, so we have the same problem how we get to landscape level. And but it's not our main goal in this project. We have to evaluate the guest catalog a bit to find some guests that are not included in the catalog, and we want to measure hopefully fine enough or good enough to prepare a kind of new emission factor for our project sites that are not included in the guest catalog. And yeah, here in our measurement in Slovinsky National Park, you see we have also a big standard deviation, but it's clear because we measure from the beginning of the day until late afternoon. So we have differences also in the plots. So and we hope we have in the end a good annual a value. We used different model approaches. Maybe one of you from of the first presentation, we see the process based modeling. We have also a very simple one. We use Michaelis-Menten kinetics and the Lloyd-Taylor approach for model the annual balances of the respiration and maybe also from the NEE or the GPP. Yeah, and our first preliminary modeling results for this ulnar scrutinoso stand in Germany. We have here a very small sink. It's all together. It's equivalence. It's not only methane, but you see here the methane, N2O, CO2, and with trees and without trees, and we see we are. It's a small source for now, and we hope with a higher water table we have a little lower the total amount so that we have also an idea, get an idea how this forest will work. Yes, I hope I'm not so long. 20 minutes, sorry. Yeah, that's it.
Thank you very much, Andreas. Are there questions, remarks? I see a question in the chat from Gert-Jan. Do you have closed chamber measurements
Yes.
at just one plot? How are you going to deal with the spatial variability?
Yeah. Yes, I think this is also another big problem because nobody has an idea how to take into account the spatial differences, heterogeneity, with a very small budget. So we have said on the proposal, okay, we can measure greenhouse gases in all countries. So we have the problem that we'd have to do it, and so we have 8 to 10 project sites, and we have to look that we have one measurement point in one of this project region. It's not much. In Estonia, we make a transect approach so that we look what are the amounts of the different gas types and go in these different gas types to measure there. And normally we have 5 to 6 plots per site to get a good overview about the heterogeneity of the sites. But again, we have 11 or big sites, 5,300 hectares in different countries, and we have only one site to measure. So it's like it is.
If there are no other questions, I would like to finalize our presentation by a word by Wojciech from Eurosite. And he will highlight one of the activities we are investigating in CarePeat is setting up a working group, a transnational scientific research group.
Hello everyone, I'm Wojtek Mróz from Eurosite Secretariat. I'm a project officer, but I had been working for a long time also as a scientist focused on dynamics of vegetation and GIS. I will not give a presentation, but just a short announcement because it is about the activity that we are planning to start, not started yet, but what is important. So within CarePeat project, we are obliged, and we'd like to do that, to create two working groups. First was already established is working group on peatland management and restoration, chaired by Paul Ledbetter from North Pennines and Carbon Connex project as well. So this cooperation is quite very fruitful. But this group rather focus on practitioners and exchange of practical knowledge on ground about different methods of restoration, whatever. We got also we would like also to create another working group which is focused on transnational research and transnational scientific cooperation. And it was create a working group just near the end of the project because nobody would cooperate then. So we would like to do it as soon as possible. And I will tell a few words about the target aims of this group and also deliverables that we would like to deliver to Interreg. First of all, we would like to prepare some publications about some scientific publications. I hope in peer-reviewed good journals and about the results of KPIT pilot project. But of course, it would be it have a special added value if it would be created in cooperation with other projects. So we are very open to share this knowledge with other scientists. And the target value is I would say just 3 publications, but of course we'll produce many more, I hope. And I've had this already started initiative of Sebastian to prepare such a publication. But by the way, and also we might have an idea maybe to contribute to one of Springer series on, and perhaps it might be a very good place to publish it in 1 or 2 years. And the second deliverable is some guest lectures about peatland restoration methods, models, business cases. The target value is 5. And of course, within the period of the project, we'll have more, but we would like to encourage all to do that. And also, we need in that group some people that are from universities to integrate these methods in school curricula. So the minimum is 3 such places that we could include in some programs. And finally, near the end of the project, we'd like to install it as a permanent group. I hope living still after the project. So this is about deliverables and how we are going to do that. So the idea is that we could have, because of course these 2 groups are somehow connected, because that is the idea, to build a bridge between practitioners and scientists. So it would be just to have them totally separately, but we think that we might organize it as a I would say something like 2 wings, so 2 task forces. One is more on practitioners, and the second on exchange of scientific knowledge on publications, etc. In future, we could organize such a parallel session with 2 task forces, and for example, later to have a kind of combined plenary the fundings. And the next meeting of our restoration working group is will be scheduled near the end of November. Celebrate in few days, and probably would like to have a kind of first meeting of a kind of core group with some people to think more about this scientific cooperation. what are the next steps? It would be great if I would find, would say something like 2 or 3 volunteers for the beginning, just to have a kind of core think tank to think how to proceed with that group. And in this group, at least from 7 to 10 research institutes. So we are thinking about some scientists with good publication track record, and people have much to do with editing, publishing in good journals, but of course not only. But I would say that we need some strong scientific partners, some universities within this group. Coming to the end, if there are already any volunteers, just you can write in chat that you'd like to start to think about it. We'll disseminate a message later on, asking some people to join that first meeting, and when we find these people, we will agree the date of first I would say kickoff meeting to start thinking about this. And of course, it is very important that this group is also responsible for cross-project cooperation. And also we had some good talks with people from Carbon Connex, with Siska and with Tuan Smith, but he left already, from also from Carbon Connex, that we could use or contribute with this group to development of C box, and also using some communication tools that they are developing within the an example that how this group could cooperate with other projects, but of course any other projects and other external scientists are welcome to join to this group. So if you have any, just write me or tell something, and if you would like to join now, you can raise your hand or write in chat, and if you'd like to join later, you can write me, because I will send a reminder about this process. So that's all from my side. Thanks a lot.
Thank you, Wojciech. Are there questions for Wojciech? I think that the group today can be a good base for the transnational scientific research group. We can work together in that group with the different projects, but also include researchers from outside our projects. See some possibilities there. Okay, now a half-hour open discussion, but we are also already running at the end of our workshop. But I think we all raised some possibilities on synergies and collaboration. So I would really like to invite the presenters to share some of the possibilities they have identified during the meeting and what they think to take up in short term. So, Laurent, maybe you can start.
Yeah, I can start. What I see, it is, I think we see different different approaches this morning, and I think we have some complementarity to find. And I think that one model can provide. It's also true. So I think we have probably to work on this connection and these links between the two applications. Also, it is important to have field data about calibration. And we see that each and we don't have the same the north or in the south of the west region. So we see that with tools, but the next step, I think, it is to provide data to the models to calibrate them. I don't know if you can say that, but the activity of the models in a potential collaboration. I don't know if it is also the same vision for the other partners.
Do you have to add this? What are your thoughts?
Yeah, I think what is very important for all of us is the upscaling from point to large scale to landscape scale. We have different tools here and approaches, and I think because this is the same problem in different issues to come from the plot scale to higher or larger scale. So maybe we have the tool that we have because in our project we find that it will be very important to get some remote sensing approaches to have a better insight into the heterogeneity of the landscape, and the wetness index is also a good maybe proxy for quantification of greenhouse gases without measurement. So maybe this is a kind of a collaboration that we go in more in the remote sensing one to upscale our whole plot area measurement, direct measurements to go one step forward in the larger scale.
Yeah, if I can add to this, I think that Laurent's work is actually somewhere in the middle between the questions that we run into in Carbon Connects and our site emissions tool, and what Andrea is pointing out on the point scale to site scale. And I can see how this mechanistic modeling approach can help to extrapolate from a point measurement information to site information. Another thing that you mentioned, Andreas, is the remote sensor. It's interesting for you to know that we're now starting up as part of Carbon Connect a spin-off project, if you will, within the project, looking at using satellite data to determine the groundwater levels. Actually, there's a commercial product around developed in the Netherlands, and going to test if this actually works, how well it works within the Netherlands first, and then we want to do this for a few UK sites. And our main objective with this is for it to see if we can actually use this in sites where we don't have that much groundwater information. Because in the Netherlands, we have, well, the land is filled with groundwater wells, so we have quite a bit of information on this. But it's not so if you go outside the Dutch borders. So that might be interesting for you, and I think we should just keep you keep all of you updated on the outcomes of this. Another thing where I see a clear connection between the projects is that one of the things that we would, well, actually two things that we feel we need to do with this site emissions tool of ours is that um, we want to test this under different situations, and that links to the second part, the second thing, which is the applicability of the guest. The guest is a central part of this site emissions tool, but it is mainly a northern German database. So I want very much like to compare these site emission tool or guest emissions to actual measurements in different sites. Actually, I've already Andre or Laurent, Andre, and I already had a talk about this. Well, I think half a year ago. So that would be one clear option for cooperation. And the other thing might be I'm more and more thinking that we need to expand on this, on what is available in guest database. For instance, to include blanket bogs and well, maybe forested situations and all that. So we could look at whether we couldn't actually expand on the existing guest database. But I do think that probably we also need to include Greifswald in this. So Greifswald is in Care Peat, isn't it?
No.
No.
No, it's not
No.
one of our partners.
Are
But
they included in any of our projects or?
I don't think so. No.
No.
But what I don't know what we on the agenda is in CarePeat. We are thinking about a capitalization project. You are probably familiar with the concept. And in such a project, you can also change the partnership and add partners. So if I Laurent can inform you better on this, on our concept idea for a capitalization activity. This activity, we would like to compare the different models and also include new pilot site areas with data that include Greifswald. We will ask them to be a possible partner.
Yeah.
Based from also from Germany, I think they find out that the water level is the best proxy for greenhouse gas measurement, not the vegetation, because yeah, vegetation had maybe 10% of variability explained, but the most important is the water level. So in my opinion, we have another project also using Sentinel data, high resolution radar data, and we tried to use this to quantify the soil moisture. And on the other hand, we have an interferometric approach. Maybe we can quantify also the vertical movement of peatlands. So to get an information about how the heterogeneity of regions work, so that we have different zones or locations with more weather conditions. And if we have this model, as not the all in the nature, but maybe we can use more the soil moisture water level because it's available. You say in Netherlands you have a lot of maybe this could be also another approach or a good remote sensing approach to use the Sentinel data to evaluate maybe approaches to quantify the soil moisture. And vice versa, then we have an idea what's happened in the greenhouse gases. Because I find good the idea yeah, it will be fine to have such maps, but we all know that nobody is measuring, so we have no ground truthing. But if we have a good model to quantify the moisture or the water level, so extrapolate greenhouse gases.
Yeah, I think there's to it. I do want to. This is not to contradict you, but to add to what you're saying. Um, 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 I've seen that in all these studies where they bring together site measurement data. What you typically see is that there's about you have a mathematical average per groundwater level or type of vegetation or whatever, and there's about 50% standard deviation with this. That practically means that the actual emissions, whichever proxy you use, the actual emissions can vary between zero base the value that we're using, which is a huge variation. So I think we still have too limited understanding of what actually drives this variation, and it's not a puzzle that will be solved very soon. So that means two things. There's a lot of work to do, but it also means that given the short timelines that we have, we need to look at this very practically and just deal with it and accept that there's a lot of uncertainty involved and try to find ways to well go forward with what we have. Well,
Hi, yeah, could I just make a quick point? I think yeah, it's going to be it's a real challenge, isn't it? How we sort of present a united front because at the moment we can't officially offset peatlands because of the uncertainty about our data and the measurements and the emissions factors we've adopted, say in the UK, go some way towards that. But it does create problems, doesn't it, with different emissions factors, different models, and which one should we it's sort of we're in danger of perhaps undermining ourselves if we present lots of different data from different models and how we try and draw it together. Yeah, I think it's really important how we try and maybe synthesize between the different models and maybe understand where different models or different systems work better and could be applied, and it might be appropriate to use different ones in different situations. I can do that, but I think it's worthwhile thinking about how we take things forward to make sure we achieve that.
Okay. Thank you. For the short term, I think it would be interesting to have another meeting between maybe CAPI partners, VHL and NABU to really talk about possible steps to take, because we can set certain goals, but then the next step is to make appointments, what is possible projects, because we all have our limited time and budget. And maybe also talk about capitalization possibilities. I don't know, Laurent, if we present our idea on the capitalization activities so that possible other interested let us know if they're interested, and then we can also talk about one meeting.
Yes, the idea was really to compare, because I think it will be difficult, as you said, to include these into actual project, because we have many things to finish. we think it could be interesting to do that more in the capital. And the idea, for example, it could be to approach on a new site, probably a very degraded site, mine, and to define the, the, the starting state, and see if our approaches are consistent, and to define the state of this business. Of course, propose some scenario to restore them, just with approaches. The idea is ready, so to continue our, then to bring together this in the capital. It can change.
So as I'm just interesting in hearing more about it, or together in this capitalization project. It is only a small. If there are interests, we can talk about it more in a one-on-one meeting. So if there are still other things people want to say? Are there still questions? Otherwise, I think we can almost close the meeting. We are running a little acceptable. No, okay. Then for participating, I think for me it's been a quite interesting workshop. So you receive all the minutes. There are a lot of names I don't know, but I will ask all the partners if they know who is participating. So I hope it will get to you somehow, somewhere. Okay, and we'll also keep you up to date on how it is progressing and when we will plan a next meeting, possible in an official transnational research working group. Thank you all.
Thanks, Catherine.
Thank you, Catherine, for putting it together.
Yeah.
Thank you, Catherine.
Thank you.
Bye-bye.
Thank you.
Bye.